Okay, I am making this video to explain the problems on our first exam, and so I'd like to go through those problems with you right now. So let's take a look at our exam problem. So the first problem on the exam was focused on looking at the relationships between various structures and identifying whether they are the same molecules or different molecules, isomers of one another, or somehow conformational changes of those molecules. So let's take a look at this first problem. If we look at this first example here, A, we see we have two di-substituted cyclohexane molecules. In one case, we have two methyl groups which are on adjacent carbons, so it's a 1,2 dimethyl cyclohexane, and the other one also is a 1,2 dimethyl cyclohexane. So there's no way it could be a constitutional isomer because all of the bonds are the same no matter where they are. The next question is, are they conformations of each other? Are they some kind of stereoisomer, or are they the same? Well, in fact, if you look, in this case, we have one methyl group that's up or axial, and another methyl group which is down and axial. Okay, and let's compare that to the other molecule on the right. And we have the same CH3 here is up and axial. But the second CH3 group on the number 2 carbon is also up on that particular position and in the equatorial position. So this can't be conformers, because if we were going to do a ring flip for this chair cyclohexane, then both of the axial positions on the left would become equatorial, and only one of them changed. So the difference here is that in the molecule on the left, let me clean this up for you. In the molecule on the left, this is the trans isomer, and the molecule on the right, this is the cis isomer. So here the methyl groups are on opposite sides, and on the right the methyl groups are on the same side. So these are in fact cis-trans stereoisomers. Okay, so that's the first problem. Take a look at the second example. We have a 5-carbon chain. In both of these cases we have a pentane chain, and we have bromine substituent and a methyl substituent on both of these. So the question is, are they different? Well, if you look at the chain and you were just to try to number and name this chain, you number from the side of the closest substituent. So in this molecule on the left, we would number 1, 2, 3, 4, 5. So this molecule is a 2-bromo, 3-methyl pentane. Okay? It's useful to be able to write the name to see if they are similar compounds or different compounds. The molecule on the right, we would also start numbering from the side of the nearest branch. So we would start numbering from the right side in this case. 1, 2, 3, 4, 5. And here what we see is that we have a 2-bromo and a 3-methyl pentane. So the name is exactly the same. So these molecules can be nothing but identical. They're absolutely the same molecule altogether. Okay, the third example here is an example of molecules which I'm showing in the Newman projection. This happens to be butane. So we have carbon 1, 2, 3 in the back, and 4. So this is a butane molecule, which we're looking down the carbon 2 and carbon 3 bond. And all we're showing here are rotational changes. So the difference here is that the CH3s are on opposite sides. The molecule on the right, to get to the molecule on the right, we simply rotate the back carbon by 120 degrees, and we would then get the molecule that's on the right. So the only difference here is that we've had a single bond rotation. They're not stuck in that position. We've shown frozen conformations, so they're not any kind of stereoisomer. They are in fact conformers. Okay, and then the last one, although you might have been misled a little bit by the fact that here we have a molecule on the left where the methyl groups are cis, and the molecule on the right where the methyl groups are trans. In fact, these are not cis-trans stereoisomers because there's another change. The change is that here we have a 1, 2, 3, so we have a 1,3 dimethyl cyclopentane, and here we have a 1,2-dimethyl cyclopentane. So we've actually moved a CH3 group from one position to another. And the relationship then between these two molecules is not just a cis-trans difference, but we've actually changed the structure, the skeleton of the molecule, and these are, in fact, constitutional isomers. Okay, let's take a look at problem 2. In this problem, what we're looking at is identifying all of the different types of carbons or hybridization in this molecule. So if you recall, the degree of alkyl substitution, if it's a carbon attached to one other carbon, it's a primary carbon. If it's attached to 2 other carbons, it's a secondary, 3 other carbons, tertiary, etc. So we look at this molecule. The first part of this question asks how many primary carbons are present in this molecule. So that has to be only methyl groups. Only a methyl group is attached to one other carbon. In this case, we have 3 methyl groups in this molecule. So the number of primary carbons in the molecule is 3. Okay. Tertiary carbons, that's a carbon attached to 3 other alkyl groups. So in this case, we have a CH2 attached to 2 carbons. That's a secondary carbon. Here's a CH2 attached to a secondary carbon. So it's a secondary carbon. This is a secondary carbon. The remaining carbons, we don't count this because it's a double bond, but this is attached to 3 different carbons, tertiary, and this is attached to 3 different carbons, tertiary. And there's one more. This carbon is attached to 3 other carbons, so that would be a tertiary carbon as well. So in this case, there are 3 different tertiary carbons in this molecule. Okay, let me clean this up a little bit. How many sp hybridized carbons are present in the molecule? Sp hybridization would require 2 pi bonds to a carbon, not just 1 pi bond to a carbon. So in this case, there are no triple bonds in which to be sp hybridized. So this question would be 0. How many sp2 hybridized carbons? Those would be carbons which have 1 pi bond to it and 3 sigma bonds. That would be the 2 carbons of the alkene. So in this case, we have 2 hybridized sp2 carbons, and all of the rest of the carbons are sp3 hybridized. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9 in total. So the answer here is 9. Okay, moving on to problem 3. Problem 3 is an acid-base reaction, and there's several things I asked in this problem. One is determine the position of the equilibrium by circling the side of the equation that the equilibrium rides on. And so if you're looking for the equilibrium position, you look for the side that is the weakest acid or the most stable species. So in this case, we have an acid on the left and alcohol on the right. You can see the pKa values for those groups. On the left, it's 4.75, which is a stronger acid. And on the right, it's 15.5, which is the weaker acid. And so this reaction lies on the right side of the equation. Okay, the other thing is I asked you to identify the acid base, conjugate acid, and conjugate base. So the species that is donating or giving up the proton on the left side of the equation is the acetic acid here. So this would be the acid, and it reacts with the other partner, which has the negative charge, which is accepting the proton. That's the base. On the product side of the equilibrium, then we have the conjugate acid and the conjugate base. So the conjugate acid would be what has the proton in the end, because if you're to do the reverse, it would act as the acid. So the alcohol here is the conjugate acid. And one clue to that is I listed a pKa value or an acid strength for that. It should give you a clue about the role of that in the reaction. And so the acetate ion is the conjugate base for this reaction. Okay, problem 4 is provide the IUPAC names for the molecules indicated, and I think people did pretty well on this problem. However, I think there was some things that were missed, particularly with regards to identifying the stereochemistry where it's a present. So if we look at this problem, there were 2 molecules here where the stereochemistry was important. That was problem B and problem, problem B and problem C. Notice there's a double bond in these problems in which you have possibilities of having cis-trans or EZ isomers. In this case, well, let's go through the naming of these molecules. In the top case, we have a 6-carbon ring, which is a cyclohexane, and attached to that is just one substituent of 2 carbons. So this is simply ethyl cyclohexane. Since it's a ring, and we define the position that the substituent is attached to as the number 1 position, is the only substituent, there's no reason to put a number 1, although it certainly wouldn't be wrong to put a number 1, although it's completely unnecessary. Okay, so ethyl cyclohexane. The second molecule has a double bond which is closest to the left side of the chain. This is a 5-carbon chain, which is a pentene, and the double bond begins on the number 2 carbon. So this is a pent 2-ene. Okay, but the double bond has stereochemistry associated with it because there's a possibility of changing one side or the other. I'll draw in the hydrogens, and it's useful to look at the hydrogens and where they're oriented here to give you an idea about the positions. So in this case, there would be a hydrogen pointing in that direction and a hydrogen pointing in that direction. And so what we see is that the substituents are on opposite sides of the double bond. The hydrogens are on opposite sides of the double bond. So this would be a trans pent 2-ene. And so you need to make sure you indicate the trans to avoid confusion with the cis pent 2-ene, which would look like this. Okay, that would be the cis molecule. In the next problem, we also have a double bond in a chain, but now what we have is a double bond that has 4 different groups attached to it. So 2 different groups on each side of that double bond. And again, I'm going to draw the hydrogen in to show you that you shouldn't miss that group on the double bond when you're considering the possibilities for stereoisomers. So in this case, it's a 1, 2, 3, 4, 5, 6, 7 carbon chain. The double bond begins on carbon 3, and then there's also a methyl substituent on carbon 3. So it's a hept 3-ene, a 3-methyl hept 3-ene, 3-methyl hept 3-ene. Okay, so that's the molecule name, but you need to indicate the positions of the highest priority groups on either side with an E or a Z distinction. So on the left side, we see that, I'm going to erase this, put the hydrogen back on. We see on the, if you split the double bond this way and look at the left side versus the right side, what we see is that the 3-carbon group here gets higher priority over the hydrogen. And on the right side, we have a methyl versus an ethyl. So if you look at your priority rules, the ethyl would have the higher priority. And so these are on opposite sides of the double bond. So this would be the E stereoisomer of 3-methyl hept 3-ene. Okay, and finally we have another 6-carbon chain. So it's a hexane with a methyl group on the 2-carbon, a methyl group on the 3-carbon, and an ethyl group on the 4-carbon. So this would be following alphabetical ordering: 4-ethyl, 2,3 dimethyl hexane. That is the proper IUPAC name for this reaction, for those molecules. So that is the proper IUPAC name for those molecules. Okay, problem 5, I asked you to draw reaction mechanism arrows to describe the electron flows in these reactions. So this is the electrophilic addition to a double bond. So we're adding HBr to a double bond in a two-step process. And I indicated here that we should have 3 different arrows. Two arrows actually belong to the first step, and 1 arrow belongs to the second step. So if we think about the electron flow, what's happening first is the proton is adding to the electrons of the double bond. So when we draw the electron flow, it's the electrons from the double bond going to the proton, and then as that's happening at the same time, the electrons between the H and Br are moving towards the bromine to break the HBr bond. That gives us addition of a hydrogen to one side of the double bond, leaving the other side with a carbocation, and the Br with the electrons from the HBr bond. Okay. In a second step, the third arrow necessary to describe this reaction is the bromide adding to the plus charge and forming a bond. So it's the electrons from the bromine flowing towards the plus charge. So that's all we were looking for this problem, was to show how these electrons flow and which bonds are breaking and being made. Okay, in problem 6, I've given you a molecular formula of C4H9Cl, and there are 4 possible constitutional isomers for this combination of atoms. So that means there are 4 different structures where the bonds are changed between the atoms. And so the way to start is just simply take a 4-carbon chain. We'll start with the simplest molecule, 4-carbon chain. 1, 2, 3, 4. That would be a butane. That's the only way you can put those 4 carbons in a linear chain. And then there's the possibility of putting a chlorine on any one of those carbons. So if I put the chlorine on the first carbon, this would be 1-chlorobutane. Now notice if I had put that carbon on the other end, so 1, 2, 3, 4, and put the carbon over here, I've just drawn it in a different way, but it's exactly the same. This is also 1-chlorobutane. We would just be numbering from the other side. So those are identical molecules. Those would not be a different constitutional isomer. So 1-chlorobutane is one example. And again, if you can name the molecule differently, it's a different molecule. In this case, they're both named 1-chlorobutane. The other possibility is to take that 4-carbon chain and put the chlorine on the number 2 position. That's a different molecule, 2-chlorobutane. Okay? And again, if I had put that chlorine on this internal carbon, that's the same thing. We just number from the other direction. Those are identical molecules. Those are not different constitutional isomers. All right, so what are the other 2 constitutional isomers? Well, it happens to be that we can arrange the carbon skeleton differently. Instead of having 4 carbons in a linear chain, we can have 3 carbons in a chain, and then one of the carbons branching off of that. And in this case, then, there are 2 possibilities for putting the chlorines. And I'll just put them here. So here, on the right, I put the chlorine on the number 2 carbon, and on the left, I could put the chlorine on the number 1 carbon. So those are 2 different constitutional isomers. This is 1-chloro, 2-methyl propane, and the molecule on the right is 2-chloro, 2-methyl propane. So you notice the names are different, so they must be different molecules. If I had put this chlorine on the left side on any one of the carbons that branch out from the center carbon, those would be all identical. Okay, so constitutional isomers of C4H9Cl. In problem 7, we're looking at answering several questions, which is the best answer related to these questions, and there are a few different concepts in here. The first one involves this terms for strain energy that we've talked about in class. In this case, specifically the term steric strain and what does it refer to. So if we look at these possibilities, A, atoms coming too close together, B, staggered conformations, C, electron repulsion between bonds, and D, compression of bond angles. Actually, B, a staggered conformation, isn't a description of strain at all. The answer is A. When atoms come too close together and bump into each other, that's what we refer to as strain energy. The other two answers, electron repulsion between bonds, is what we would refer to as torsional strain, and compression of bond angles would be angle strain. Okay. In the second part, which of the following would be an example of a Lewis acid? And so remember, a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. Methane can do neither, so you should be able to rule that one out. Water and ammonia are molecules which contain lone pairs, so those generally react with things as a Lewis base. Like we had on the quiz, we had a nitrogen-containing compound. It was the Lewis base. The only possibility here is boron trifluoride. It has an empty orbital because boron only has 3 valence electrons to start with, and it can only form 3 bonds, leaving behind an empty orbital in an unfilled valence shell that would accept electrons by forming a bond to something that could donate, like ammonia. So the BF3 or A is the correct answer for a Lewis acid. The third part of this, which of the following statements about secondary carbons would be false? So a secondary carbon, as we had talked about before, is a carbon which is attached to 2 other carbons, so that has to be true. A secondary carbon has 3 hydrogens attached. That has to be false because if it was secondary, there would be only 2 other positions that weren't carbon. So it would be no possibility for 3 hydrogens. So the answer here was B. Okay, in problem 8, I've given you the names of molecules, and I'd like to draw the structures of those molecules. So in the first case, we have a molecule which is a cyclic alkane, so cyclobutane, that has 4 carbons in a ring, with a chlorine on the number 1 carbon and an ethyl group on the number 3 carbon. So the way to do this is to simply just draw a 4-carbon ring and put those groups on. And notice I indicated the stereochemistry because if there are 2 substituents, the chlorine and ethyl can be on the same side or opposite sides. So in this case, I put them on the same side. And you could do it several different ways. If I draw the chlorine, if I draw the chlorine up with a bold, that's where you demonstrate clearly with a bold line. I could draw the ethyl group with a dashed line indicating that it's down. That would be trans. Alternatively, I could have just flipped the molecule over and put the chlorine down and the ethyl up. That would be identical. But these are in a 1,3 relationship, so that's the structure for 1,3, 1-chloro, 3-ethyl cyclobutane in the trans configuration. Okay. Next one is an 8-carbon chain. Let's see what I have here. 1, 2, 3, 4, 5, 6, 7, 8. There's the octane, in which we have on the 6 carbon an ethyl group, and on the 2, 3, and 4 carbons we have methyl. So there are 3 methyl groups. So that's 2, 3, 4 trimethyl octane, ethyl on the 6 carbon. Okay. Moving on to the next ones. Again, we have a molecule with a double bond, and I've indicated that this molecule has the Z geometry, so you need to pay attention. A double bond that would be E would have the highest priority groups on opposite sides of the double bond, and the Z would be the same side. So what I'm going to do is draw hept3ene with 3-methyl. I'm going to draw it down here. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, the double bond would be here, and the methyl group would be here. And then we have to figure out, and I'm going to draw again the hydrogen, which isn't indicated. And look at that, the way I've drawn that double bond is at the Z geometry. Well, in fact, the highest priority group on the left side is the ethyl, and the highest priority group on the right side is this propyl. So when I look at this, these are on opposite sides of the double bond. So this, what I've drawn here is the E isomer. So I've got to change this. I've got to draw the Z isomer, which means I either switch the two groups on the left side, or I switch the two groups on the right side. So I'm going to switch the two groups on the right side. So instead of drawing it down from this point, I'm going to draw the 3-carbon chain up. That would put the hydrogen down and the methyl group down in the orientation I've drawn it there. Oops, that would be a methyl group. I'll draw it out. The methyl group in the orientation. So now the groups that are highest priority are both on the same side of the ring. Okay. Lastly, we have 1 bromo, 3 ethyl, 2,3-dimethyl pentane. So a 5-carbon chain, 3, 4, 5, with a bromine on the number 1 carbon, methyl groups on 2 and 3, and then another ethyl group on number 3. So that would be the structure for 1 bromo, 3 ethyl, 2,3-dimethyl pentane. Okay, in problem 9, I've given you a reaction energy diagram describing a 2-step reaction and asked you to identify the pieces of this reaction diagram related to the general reaction I've drawn above. So this is a reaction of a molecule A in the first step converting to molecule B, and then a second step converting to molecule C. So hopefully the first part of this problem was not difficult for you. You start with A on the left, it goes to an intermediate B in the middle, and the final product would be C on the right. Okay. The next question is to draw an arrow showing the activation energy for the slowest step. And so in class we described this by showing the energy difference with an arrow. The slowest step is the one with the highest activation energy. So if you look at the reaction from A to B, that activation energy is here, and that's the correct arrow answer I was looking for. The activation energy from B to C is actually only this much. So if you start from B and go to C, the activation energy to do that is very small. So the slowest step is the one with the highest energy hill to go over. That would be the step from A to B. The last part of this problem was to draw or circle around all of the transition states. So a transition state is the point at the highest part of the graph. So there's a transition state, and there's a transition state. The transition state between A to B here, and the transition state between B and C here. This is not a transition state. B is actually an intermediate. It's the bottom of an energy well, a local minimum. And that's describing actual intermediate in a reaction, not a state of transition between two species. In the last problem, problem 10, I wanted you to identify which in each of these pairs of molecules, the structure which is the lowest energy or the most stable. In part A, we look at 2 different conformations of 1,3-dimethyl cyclohexane. In the first one, they are both axial, and in the second one, they're both equatorial. And as we discussed in class, equatorial positions have more space and freedom. There's less steric strain. So in fact, this one on the right would be the most stable of that pair of molecules. In part B, we have 2 conformations of butane, one in which the 2 CH3 groups are as far apart as possible, and in the other, those 2 CH3 groups are coming closer together. They're both staggered conformations, but the one on the right would have more strain energy from steric strain. So in this case, the molecule on the left in B is the one which is most stable. In example C, we look at a cis-2-butene versus a trans-2-butene, and a similar thing, the CH3 groups being on the same side of the ring are more sterically crowded than having those CH3 groups on the opposite sides of the double bond. Sorry, not ring, double bond. So it is the trans isomer which is the most stable or lowest in energy. And finally, we have 2 rotational conformations of butane. Again, in this case, we have staggered conformation, which is the lowest energy state, which is the one on the left. This one is higher energy because they're eclipsed and we have all this torsional strain from those bonds eclipsing. The bonus problem, I asked to describe how cis-trans isomers are important for our ability to see. If you recall, I talked about this example in class where we get beta-carotene in our diet and it is converted into retinal, which is embedded in a protein in the back of our eyes, in the retinas of our eyes. And when it absorbs a photon of light, it undergoes a trans to cis isomerization, which changes the structure of the protein it's embedded in and provides a signal to the optic nerve that says our eye has detected a photon of light. That is how isomerization of double bonds is important for our ability to see. I wasn't looking for that level of detail of information. I was hoping you would say something about maybe retinal or beta-carotene and that the double bond isomerizes when light hits it. If you said anything about that, you were given some extra credit points for that problem.